Hello and welcome to our third video about tropical cyclone motion. In this video, we're going to introduce this concept of the beta effect. What is beta? What is its effect? And how does it contribute to tropical cyclone motion? So let's dig in. So hurricanes or tropical cyclones more generally don't exist in a vacuum. They don't just exist at a single point. They exist over a horizontal area. And in this case, we're particularly interested in the north-south extent over which tropical cyclones exist. So here's an arbitrary tropical cyclone at some arbitrary longitude. Here's three different lines of latitude, 14 north, 17 north, and 20 degrees north latitude. So there's flow on either side of the tropical cyclone from north to south or south to north. So the key idea here is that latitude and thus the value of the Coriolis parameter, which is related to latitude, varies in the north-south direction across the cyclone. In particular, that Coriolis parameter has this value 2 times omega, which is our 7.292 times 10 to the minus 5th radians per second, times the sine of the latitude. So as you go to higher latitudes, the Coriolis parameter gets larger. We define this concept of beta as the meridional variation, the north-south variation in the value of the Coriolis parameter in the y direction here. So as you go along the positive y-axis from south to north, because latitude increases, the value of f also gets larger. So we can define these latitudes as having Coriolis parameter values of f0, f1, and f2 that we see here. Because f2 is greater than f1 is greater than f0, beta is always positive in the northern hemisphere. You can think about whether this would be true in the southern hemisphere, but I'll leave that as a thought exercise for you to consider. So just as we did for large-scale tropical cyclone motion, let's take a vorticity tendency look at this idea of the beta effect here. So if we use a very highly simplified form of the vorticity tendency equation, where this left-hand side here describes the local change of relative vorticity or cyclonic rotation with time, we have one forcing term here, given that we're making the assumption of a uniform wind field with height, whether that be with the cyclone itself or the large-scale steering flow impinging upon this. And this is an advection term, minus the velocity vector v dotted into the gradient of some scalar quantity here. And in this case, that scalar quantity is the relative vorticity, so the rotation associated with the wind, plus the planetary vorticity, f, that we see here. We can distribute this advection operator to each one of these terms, and we get the two right-hand side forcing terms. The advection of relative vorticity, which we can view as the motion of the tropical cyclone governed by the large-scale wind, and the advection of planetary vorticity, which, as we'll show in just a moment, is our beta effect term. Because the Coriolis parameter only varies in that north-south direction. So if we break this down, we get a minus u partial f over partial x, minus v partial f over partial y, and if we had a vertical term, we'd have that there as well. However, Coriolis parameter only varies in the y direction. And so consequently, it's only that minus v partial f partial y term that is retained from expanding this advection term. The partial f partial x and partial f partial whatever your vertical coordinate is, z or p, go away. And so consequently, we're left with this advection of relative vorticity, the large-scale steering flow, minus v partial f partial y. But in our previous video, we defined this quantity, partial f partial y, as the beta parameter, which we said is positive definite in the northern hemisphere. So we can rewrite this as our relative vorticity advection term minus the beta effect term that we see here. So this term is going to govern the large-scale flow's influence on where the tropical cyclone goes, and this is going to govern the beta effect on where the tropical cyclone goes. So we're going to make the key assumption here, just as we did in the previous video, the tropical cyclones move toward regions of where the vorticity is increasing. So whatever the steering flow may be, if that steering flow is going across the cyclone, you would expect there to be a positive tendency downwind of that steering flow and a negative tendency upwind of that steering flow. So we're going to assume that wherever the wind is causing the cyclonic intensity or cyclonic rotation to increase is where the cyclone is going to go, assuming that the cyclone itself isn't changing in intensity and thus changing its value of relative vorticity. So coming back to our diagram here, we're assuming that there's no large-scale horizontal flow, such that there is only flow associated with the tropical cyclone itself. We have our 3 different lines of latitude with 3 different values of the Coriolis parameter corresponding to each one of those latitudes here. And we have a blue arrow depicting here, which will indicate the direction in which we're going to show that the tropical cyclone is going to move due to this first component of the beta effect. So we're going to break this beta effect into 2 components. The first one that we're going to describe here is this idea of a linear beta effect, resulting only from the flow around the tropical cyclone and how that changes the planetary vorticity through advection to its west and to its east. And I'll specifically note it's not changing the planetary vorticity to its west or to its east, but rather it's changing the relative vorticity through the advection of planetary vorticity to its west and to its east. So we put in arrows to depict the large-scale flow associated with the tropical cyclone for the northern hemisphere from north to south to the west and from south to north to the east here. So to the west, the wind is going from higher latitude toward lower latitude. So it's going from higher planetary vorticity toward lower planetary vorticity. So it's going to try to bring higher values of planetary vorticity toward the south. Whereas on the east side, the wind is blowing from south to north, from lower values of planetary vorticity to higher values of planetary vorticity. So it's going to try to bring lower values of planetary vorticity to the north. So this would give us a positive and a negative vorticity tendency due to the beta effect term alone to the west and to the east of the cyclone here. So specifically, if we look at this quantitatively, the meridional component of the wind to the west is negative. It's directed along the negative y-axis. So V is negative. Beta is positive. So leading negative times negative gives us a quantity that is positive. In other words, our cyclonic vorticity, relative vorticity, is increasing to the west. On the east side, the opposite is true. The flow is from south to north or along the positive y-axis, so V is positive. Beta, of course, is positive once again, but this leading negative, negative, positive, makes the whole thing negative, which means that our relative vorticity tendency is negative in this case. So assuming no large-scale horizontal flow in this case, we're going to direct the tropical cyclone from east toward the west, toward this area of positive or cyclonic vorticity tendency that we see there. So we can put this into a numerical model and look at how this actually causes the cyclone to move. We start off here at t equals 0, and the red contours here are measuring a quantity called stream function, a measure of rotational flow. They get more negative as you go in there for the cyclonic flow that we see in this particular example. And these are concentric circles here at the initial time, centered at 0, 0 on the x-axis and the y-axis. The distance between every adjacent point on each axis is 200 kilometers. If we go out a day and a half or 3 days, note that the center of that feature moves ever so slowly to the west. Here at 72 hours, it's still along the y equals 0 line, but it's just to the west of the x equals 0 line. So this is a very slow motion from this linear portion of the beta effect that we see here. The thing that really stands out more than that, however, is this transition away from a concentric circle structure for stream function to something that is biased toward the west and crunched up on the east side that you see especially here at 72 hours as a result of this beta effect. This is because the cyclone near the center is relatively small, but as you get to larger radius, the cyclonic circulation gets larger. The wind gets weaker, but the horizontal extent in the X and the Y directions gets larger. So out 400 kilometers from the center of the storm, you're going to have a greater flow from north to south, or in this case for you guys, south to north or north to south here on the west side. So you're going to have a greater change in planetary vorticity because you're covering a greater distance in the north-south direction associated with the cyclone. And so consequently, you are increasing the cyclonic portion of the stream function to the west and decreasing it to the east. So that's why you get this kind of bulge out to the west that you see here and crunching up on the east side. So it changes the cyclone structure just a little bit while causing a very slow westward motion. But this isn't all there is to the beta effect. We also have this component of the beta effect that is nonlinear. So we start with where we left off with the linear component of the beta effect here. There's no large-scale horizontal flow, and the flow around the cyclone itself leads to a positive and negative relative vorticity tendency to the west and to the east of the cyclone, which gave us our slow westward steering current. But because of these changes in relative vorticity that we kind of saw with the stream function on the previous slide, the flow becomes more cyclonic here to the west and more anticyclonic or less cyclonic here to the east. We can conceptualize this as creating vorticity anomalies with their own anomalous flow fields that contribute to tropical cyclone motion. So for instance, this positive vorticity tendency to the west that increases the cyclonic rotation there is associated with this anomalous cyclonic rotation depicted in the green arrows that we see here. Conversely, to the east, this anticyclonic vorticity tendency or negative vorticity tendency here is associated with anomalous anticyclonic or clockwise flow here to the east. So between these two, we have flow directed from south to north. And so this flow is going to go across the cyclone and try to push it toward the north. And that's where we get this blue arrow here. So the full beta effect is the combination of these two forcings. The one associated with the cyclone's winds itself, leading to a vorticity tendency that is positive to the west and negative to the east. So that pushes the cyclone toward the west. However, that vorticity tendency itself has a feedback upon the steering flow as well that causes the cyclone to be pushed toward the north. So you have a northwestward motion associated with the beta effect, the linear and nonlinear components that is manifest across the storm. And we see this in our numerical simulation results. We start from the same place with the same vortex as before at t equals 0 hours. As we go to 36 and 72 hours here, note that it progresses both north and west. Here it's roughly at about 4 to 5 on the y-axis and about 3 to 4 on the x-axis. Over the course of 3 days, it's moved several hundred kilometers. This is leading to a total component of steering that is on the order of 1 to 2 meters per second associated with the combination of the linear and the nonlinear portions of the beta effect. Relative to the overall tropical cyclone motion that's on the order of 5 to 10 meters per second, this lies close to about 10%, sometimes a little more, especially for the slow-moving storms, sometimes less, especially as you get to higher latitudes and you start looking at motion that is 20, 30 meters per second in some cases. But on average, it's roughly 10%, 1 to 2 meters per second of a cyclone's motion. And in the northern hemisphere, it is this northwestward drift or motion at that 1 to 2 meter per second threshold. We can look at this in a vorticity versus stream function perspective here as well. We're looking at 36 hours here, and the blue dashed contours in here are associated with the cyclone's relative vorticity. So this is a maximum here at 0, 0 on the axis in this particular case, and the values get smaller as you go outward from there. The magnitude of cyclonic rotation gets smaller as you move away from the center of the tropical cyclone. The red contours are the stream function, which is very closely related to, but not identical to, the vorticity. And note how the center of these is offset somewhat from the center of the blue contours. These red circles are not concentric with the blue dashed circles. They're offset a little bit to the west from that center. So if you envision the total wind field being associated with the stream function, looking at these like streamlines, as we note here, we see a flow that is directed toward the northwest, given by this blue arrow that I've depicted in here, in association with this beta effect. So what about for realistic tropical cyclones? To this point, we've assumed that the tropical cyclone's intensity is constant with height. But we know from our tropical cyclone structure lectures that tropical cyclones are not constant in intensity with height. Rather, they weaken as you go upward in height. And so consequently, the magnitude of this purple flow is going to weaken as you go upward with height, which will lead to a reduction in the magnitude of these vorticity tendencies with height, which will then lead to a reduction in the magnitude of their induced horizontal flows with height. So what you see here might be appropriate for the surface, but as you go to higher altitudes, that steering flow around the cyclone becomes weaker, the vorticity tendencies become weaker, the associated flows become weaker, and consequently the direction of component of steering toward the northwest becomes smaller. So there is a vertical variation in the magnitude of this beta effect that would lead to some tilting of the vortex over time, but if you average that beta effect out in the vertical, you end up something that's a little bit weaker than what you saw in the numerical model results in the previous slide, something closer to 1 to 2 meters per second rather than the 3 to 4 meters per second or so that the previous model results might have implied. So there are a lot of sensitivities in terms of the beta effect. Cyclone intensity is going to lead to variations in the beta effect. Cyclone size, its expanse of cyclonic flow, will lead to some variations in what we've shown here. Its latitude, given the dependence of the Coriolis parameter on latitude relative to the sign of the latitude, will lead to a difference in terms of the magnitude of the beta effect. And whether you're in the northern or southern hemisphere, that modifies the sign of the Coriolis, that modifies the sense of the relative vorticity or rotation there. I leave these as thought exercises for you to consider, and in fact the discussion forum post for this week, for this module, relates to picking at least one of these and stepping through them to describe what effect does a weaker or stronger intensity, a larger or smaller cyclone, a lower or higher latitude storm, or one in the northern or southern hemisphere have on the magnitude of the beta effect that we have demonstrated here. So I encourage you to step through those because you never know when those types of questions might come up once again. So wrapping up here, just to reiterate, the beta effect is about 10% or less than 1 to 2 meters per second of a tropical cyclone's motion. Together with the large-scale steering flow, which we considered in our previous video, we're looking at something on the order of 70 to 90%, a very large percentage of the total variation in tropical cyclone motion being explained by these two processes here. This beta effect, which owes its existence entirely to the north-south variation of the Coriolis parameter across the cyclone, imparts a northwestward steering flow in the northern hemisphere, a very small westward and a larger northward steering flow for the linear and nonlinear effects, respectively, across that tropical cyclone. Because tropical cyclones weaken with increasing altitude, though we didn't tie this specifically back to the math, we could do so in the conceptual framework that we did a couple of slides ago and show quantitatively and qualitatively that the magnitude of the beta effect also decreases as you go upward within a tropical cyclone. So that's it in terms of the beta effect. As we get to our next video, which is the last in this series and the last in the semester, we're going to discuss other less significant factors that influence tropical cyclone motion. Each one of these is on the order of a couple of percent to a few percent, or applicable only in very specific circumstances. But until then, thanks for tuning in.